From ContainerDays Hamburg, this video is proudly presented by Dux IT.
So my name is Antonia, and this is my friend Simon. And we want to talk a little bit about Kubernetes at the edge today. And we're also going to have a little demo, which may or may not work, so it's a little bit exciting. I hope you're all looking forward to it. So first, I'm going to start by introducing edge computing for those who may be uninitiated. We're going to look at some use cases before going into a specific project, which is KubeEdge, which we are also going to demo. And then we want to root all that a little bit back into reality before maybe having a little discussion at the end. So edge computing, what is that? According to Gartner's glossary, edge computing is part of a distributed computing topology where information processing is located close to the edge, where things and people produce or consume that information. Okay, so we have information that is produced somewhere. One such place where a lot of information or data is produced, among other things, is a factory. So in this picture, you can see a factory, and you can also see a couple of clouds. And you have to think about the source of information in this factory as things like sensors, actuators, robots, and so on. And those are referred to as IIoT devices, so Industrial Internet of Things devices. And traditionally, you would send all the data that is produced by these devices up to the cloud for processing. However, there can be a case where you have a very slow process, or it's very expensive, it's too much data, it's not possible for some reason. And so you introduce this additional layer between the cloud and the device, which is called the edge. And as you can see here, at the edge, you have a couple of machines, some sort of servers maybe, and you have to think about these as being physically close to the device. So they would be in the same network. Now, why would you want to do this? There can be a couple of reasons for that. Here's 4: latency, bandwidth, autonomy, privacy. And specifically, you might have an edge device which is a self-driving car, right? So in that case, you really don't want to have any latency when there's some decision that needs to be made. Or in case of bandwidth, if you just have large quantities of data, you just cannot stream all of them. It would be better to do some pre-processing before you send all of these to the cloud, right? And in case of autonomy, what we mean by that is that your factory can be in a really remote location, like it might be somewhere in the mountains, so your network can be down a lot of the time, but you still want things to work properly. And then at the end, you might just not want your data in the cloud for some reason, or privacy. There can be some sort of regulation why it's not allowed, or you're just worried about user trust, and so on. And all of these are valid use cases for edge computing.
Okay, yeah, so let's now take a look at some practical applications of edge computing, so maybe we make it a bit more relatable and understandable. So here we've got 6 areas that we've drawn up. They're areas that are sort of heavily relying on edge computing already. Not an exhaustive list, obviously, because new industries, new use cases are being added all the time. Just to pick a couple of my favorites off there, if you look at the smart cities, the responsive public transport, that's quite clever. You're sort of running analysis on CCTV footage to detect where traffic backups are, or maybe where demand for a service is quite high, and you reroute your your services accordingly to meet those demands and to work around those bottlenecks. And then down in the healthcare section at the bottom, the in-ambulance data processing. So you've got a patient that's on their way to the hospital, their conditions being monitored all the time in the ambulance. That data is then being fed back to the hospital in real time. So the hospital's sort of ready, they're prepared for when the patient comes in and they know what the up-to-date situation is. So it cuts down on that handover you have. Maybe they might miss some information. It sort of cuts out that problem. So yeah, there's quite a bit on there. There's quite a lot of use cases, and I said there's more of them coming all the time. Let's have a look at a couple of specific case studies that we've got. So the first big success of KubeEdge was in China, where they overhauled the electronic highway toll collection system across about 85% of China's provinces, their cities, and their sort of autonomous regions. And the old system used to be your typical toll plaza where your vehicle drives up, stop at a barrier, pay their toll, and off they go again. Obviously quite slow, and it can cause bottlenecks. And these were managed all individually and by local organizations. This has been replaced with overhead gantries everywhere. So they've all run cameras, and those cameras are doing license plate recognition. So they're tracking who's using the road when, and just billing them accordingly. And this new system has around 100,000 edge nodes, and runs about 500,000 edge applications across all these edge nodes. And it's generating and processing around about 300 million data points every single day. And it's estimated that at toll plazas, which obviously no longer exist, this has improved traffic efficiency by about 10 times. So another use case that I find quite interesting is the first cloud-native satellite. So your traditional satellites, they're capturing data, they're storing it locally, and then they transmit it back to Earth as and when they can, due to bandwidth or the connectivity. And this is going to hit some limits if you produce too much data to be able to transmit, because obviously satellite links aren't the fastest. So in 2021, China launches their first satellite, which is connected back to the ground via KubeEdge. And this satellite's being used for flood prevention and disaster mitigation. So previously, a flood happens, some disaster happens, someone would task a satellite to go over, they would image the area, that data set gets sent back, a person looks at the pictures and produces a report. This is quite a slow feedback loop. And the main problem with this is that a lot of these incidents in China happen in mountainous regions, and of course they're quite commonly covered by cloud. So it's not particularly useful when you get a photograph back that you can't see anything from. So that time is wasted, and the bandwidth used to transfer it is wasted. So this new satellite, it runs a small AI model on board. It's not particularly complex, but it's able to identify how much of the photo is covered by cloud. And it can also do things like analyzing water levels to see whether flood levels are increasing or receding. And based on what it decides, it then determines if the images are worth transmitting down to the base station. And then it goes through the same process. The data gets processed on the ground. They're running more powerful models on the ground on the same images. But this time, reports are also compiled automatically. So it's much, much quicker. The feedback loop is much shorter. And it's reduced the disaster response from days down to hours. And they estimate that it's also reduced the amount of data being transferred down from the satellites by around about 90%. So quite a significant saving. There are a bunch more case studies that are available on the KubeEdge website if you want to take a look at those. I'll leave that up there for a moment if anyone wants to take a photo of that. Okay, so the talk, obviously, you come to see is about KubeEdge, and we've covered Edge pretty well now, I would say. So now we want to talk about where Kubernetes factors into the equation. So you've got a bunch of different challenges of working with edge computing, but the main problems are scale, connectivity, and lifecycle management, so updates. So obviously, running workloads at the edge is pretty different to running it in the data center. As we said with the highway toll collection use case, scale is pretty big. You could have thousands or possibly even hundreds of thousands of nodes and devices. And they're also spread across many geographic locations as well. And these nodes are quite often quite small, quite resource constrained. They're remote, as we said, and they're also sometimes just offline, depending on what their connectivity is. If it's cellular, you can't rely on that. You can't necessarily rely on any type of connectivity with these edge nodes. But through all this, we still need to update and patch them consistently for CVEs, or maybe your software just needs an update. And this is kind of difficult when connectivity is unreliable or not there. So Kubernetes, obviously, it can address a lot of these things in traditional IT, and I'd imagine most of us are quite familiar with it at this point now. So it's declarative. We say how we want the system to look. It makes it so. And it is portable in that you can run these apps on your laptop, on your developer's laptop. You can run them on the edge. You can run them in the cloud, in the data center. It's much the same thing wherever it is. And it's also automated, tying back into the first point. It reduces the manual operations because most part, you've got controllers that are doing the work for you. It's not a human. And lastly, it's familiar. It's the same thing. There are some differences in different places where you run it, but it's Kubernetes everywhere. It's much the same, and everyone's pretty familiar with that by now. But vanilla Kubernetes assumes that you've got nice, fairly fast, stable data center networking, and as we've already said at the edge, that just doesn't happen quite a lot of the time. So as a result, we need a solution that can handle this and can work around the limitations. So this is where KubeEdge comes into it. So the idea is it offers resilience and features that enable you to support edge deployments with these caveats in mind. So let's have a quick look at KubeEdge itself just briefly. Started back in 2018 by Huawei, so it's been around for a little while now. And their stated mission is to extend Kubernetes to edge nodes and IoT devices. So some core features that it has, it manages workloads on the edge nodes, but it's doing them via standard Kubernetes APIs that we already know, so it's not like some hugely different model that you need to understand. It handles unreliable or potentially unreliable long-haul connectivity back to the clusters, and you can manage devices connected to these edge nodes through the device twin model, which we'll talk a little bit about shortly. So quite heavily adopted by the community already in retail, telco, and industrial sectors. And it entered the CNCF as a sandbox project back in 2019, so not long after it was started. It was incubating in 2020, and it actually graduated late last year. So with that all said, I'll hand over to Antonia for a little bit about the architecture.
Okay, so I want to talk a little bit of a broad kind of overview before going into details. So let's start with that. You might recognize this cloud edge device trifecta from the earlier slides. Of course, in this case, when you look at the cloud layer, it might not necessarily be actually the cloud. This could be any Kubernetes cluster. It could be on premises, and I guess many times it is. So the first component you will see on the cloud layer is the cloud core. And this is actually the entry point from the Kubernetes cluster to the edge. So all of the communication from the Kubernetes API to the edge is going to go through here. The cloud core actually connects to the edge core on the edge layer. And one edge core is running on each edge node. So you see one here, but there could be thousands of them. And again, these could be satellites or toll stations or all manner of things. Then the edge nodes actually join the Kubernetes cluster by connecting to the cloud core. So they're going to look like a normal Kubernetes node. They have a special label on them, so you can schedule workloads there. The edge core is installed on the machine as a single binary, so it's comparable to K3s. The edge core talks to the device layer via MQTT, and it also talks to local applications at the edge via HTTP. And then at the device layer, you have actual devices. So again, these are sensors and robots and so on. KubeEdge offers a framework where you can represent these devices as custom resources. And to make the whole thing a little bit easier to read, I actually marked the Kubernetes API-related streams here in blue and the ones that are relating to devices in red. So you might notice that also in the following slides. So I want to look a little bit more detailed next. Let's start at the top with the cloud core. So the cloud core is installed as a Helm chart usually, and there is an upstream CLI tool which is called KeyADM, which you can use to do that. The cloud core has a couple components. First, you see here the Cloud Hub, and the Cloud Hub is essentially a messaging broker, so it keeps open a secure, persistent channel via WebSockets or even Quick to each of the edge hubs. Now you can see that we also have some controllers running in the cloud core. The first one, the blue one, is the edge controller. And that one propagates changes to workloads running at the edge from Kubernetes API to the edge. So it is basically managing workloads. And in the opposite direction, it will update statuses and events and so on from the edge back to the Kubernetes API. Then the red one, the device controller, is the one that reconciles device CRs. So it will sync between Kubernetes custom resources and managed devices. Now, all of the communication, as I mentioned, goes through the Cloud Hub to the edge. And this communication channel has a few features. One of them is load reduction. And this is happening by aggregating updates. So you don't actually receive updates from all of your 100,000 toll stations or what it was. They're going to be aggregated so as not to overload the Kubernetes API that much. And then it will also maintain resilience across flaky networks, and it does so by doing incremental updates. So in case your Kubernetes node is disconnected and then it reconnects, you're not going to get flooded with all of the updates all at the same time, but instead it's going to be incrementally. Like this, you can actually integrate the edge quite easily into an existing Kubernetes cluster. And it has been shown, as Simon mentioned, that 100,000 nodes could be integrated in that way, which is quite impressive. Let's take a look at the edge core as well. Now, the edge core also has an edge hub, which is the counterpart of the Cloud Hub, and the link to the cloud. Again, this is via WebSocket or Quick. And it will route all of the messages from the cloud to the correct edge modules. It's also going to report things like node status and device status back to the Kubernetes API, takes care of things like keep alive, and also routing messages within the edge. There are two important modules that you can see here, which both deal with the local state, and one of them is called Meta Manager, and the other one is called Device Twin. Now, the Meta Manager is a cache and message processor, so it stores data like pod state, config map contents, and so on in a local database. So this is a lightweight SQL-Lite database, and the reason is so that your node can still function when it's offline, and then later it's going to sync any changes when it reconnects. And then the Device Twin keeps track of the state of devices. It manages attributes and status of those devices, and it will sync that information both to the applications that are running locally, but also to the cloud. The next component you can see is called EdgeD, and you can think of EdgeD as the kubelet of the edge core. It manages lifecycle of pods, it talks to the container runtime, and makes sure that you can schedule workloads on the edge node just like you would in any of your cloud nodes. It also handles other resources such as config maps and secrets, which might be locally cached. All of the communication at the edge goes through this common messaging protocol called Beehive, which is marked in yellow here. I hope this is readable because it's quite bright. On top of that, you have two buses. The first one is the event bus, which integrates with MQTT, and it connects edge modules and device mappers, which in turn connect to actual devices via device protocols, which we're going to see a little bit later, and the service bus, which provides HTTP communication with local apps and APIs. You can see a little bit at the bottom on the left that there's a container runtime, which I already mentioned, running pods under the control of EdgeD, and a mapper next to it, which translates between device protocols and KubeEdge. And all of these together allow edge nodes to keep running workloads and manage devices, even when the cloud connection is unreliable. It's all good. Your cloud core is installed on the Kubernetes cluster. All of your edge nodes have joined using the edge core. So you already have a valid use case here. You already have extended your Kubernetes cluster to the edge, and we can just stop. But we won't do that, actually, because there are some additional capabilities in KubeEdge that we wanted to try out, which are for the device layer, and that is where we get into the IIoT territory. In this layer, it's actually all about protocols. So any IIoT device is essentially a thing that generates some sort of data. And you have various sources, some sensors, some cameras, and all of these are going to expose the data with various protocols. It could be Modbus, OPC UA, MQTT. There's few here, but there are lots more. And I mean, you may have seen something like this before. If you have, like, for example, some iKey temperature sensor in your house, you use maybe like Home Assistant, connect with Zigbee, and so on. This is essentially the same thing. All of this data that you get from your sensors, you're going to want to consume that with some app. And in order to do that, we need to bring this data into KubeEdge. And this is where the mappers come in. So mappers are translators between the physical world, device protocols, and the KubeEdge logical world. And in the industry, this is actually often called an adapter. So in HiveMQ Edge, you may have seen this as an adapter. But in KubeEdge, these are called mappers. And the reason is that they map some obscure industrial protocols to something that KubeEdge can actually understand. The mapper contains some business logic to communicate with devices in a specific protocol, and it will run on a regular container on the Edge node. Now, when the mapper starts up, it will register with the Edge core as a usable protocol. There's a framework available upstream that you can use to implement your mapper for any protocol that you like. There is some implementations already available. The mapper will collect some data from the device and transfer that to KubeEdge through the MQTT broker that is running at the Edge core. The devices, as I've mentioned before, are represented as custom resources in KubeEdge, and those are installed with the Cloud Core Helm chart. The first one, the device model, contains properties and capabilities of a specific device type. So this could be something like Philips Hue model XYZ, and then the device instance is an actual device at a specific location. So this is then going to be your personal Philips Hue XYZ, which is in your living room, for example. But I want to try a more industrial example here. This is Advantech Adam 6017, and I've never touched one of these in my life before. However, let's try. So this has 8 channels, which are mapped to Modbus registers, and you can connect sensors to these 8 registers. Here on the left, you can see the device model CR for Adam 6017. As you can see, at the bottom, we set the protocol to Modbus, and then we have 8 channels in our properties. I know you can only see 2, but there are 8. And we can find the addresses for these in the user guide of the device, which you can see on the right. So we look these up, and then we put them in the second CR, which is the device instance CR. You can see that this references the previous one in the device model reference, and then we have protocol properties to access the device, which map each property to a register using the values from the user guide. This CRD actually has some more fields than this, so you can push data directly to MQTT or some other endpoints. It's a little bit out of scope right now. In fact, the whole mapper interface is quite extensive. You can look up upstream about the inner workings of the mappers, and you can implement your own in Golang. However, it is a little bit too much information for this talk. So instead of that, we just going to look at some demo.
Why not? Okay, yeah, so we've got a fairly basic demo here, but the idea is that we're trying to showcase the whole KubeEdge stack so you can see everything working together. So I'll explain a little bit about how it's going to work first, and then we'll get into it. So there's this lovely screenshot of my colleague Xavier here demonstrating what it's doing. So we've got this webcam here, which is connected to a Raspberry Pi, and that Pi is joined via KubeEdge to a Kind cluster running on the laptop at the moment. And so the idea is that when you're in front of the camera and you raise your hands, it's going to update a device custom resource which we've got in the Kind cluster, and that's going to hold the number of raised hands which the camera is detecting. So we have a Python app which is running on the Pi. Oh, that's a good start. Python app running on the Pi, and that processes the feed that the camera is delivering, and then that's using media pipe framework, and that's a framework from Google, which is able to identify postures in humans. And the idea is, you can see it's creating a shoulder line, or where it judges a rough shoulder line, and then when it senses what it thinks is a hand above that line, that obviously gets added as one that it counts. We're running this as a container on the Pi, so we don't get this visual feedback. You run this, if you run it on your laptop, you get this. So we've got no visual output, so we can't see what it's doing, but instead we've got a Grafana dashboard, which in theory is updated in near real time. We'll see how that goes, because the lighting is, I think, possibly going to confuse the camera a little bit, but we'll see how it goes. I'm just going to drop out of the presentation and see if we can see this, this dashboard working. Where are we? So if we shift that over there, oh no. If we pop that over there we go. So we've got no hands raised at the moment, so I don't know how this is going to go. We will see. We're not quite sure. It's only a standard webcam, so we're not sure how well it's going to pick people up. I think maybe it might be a good idea if we had some willing volunteers to come a bit further down the front so they get a bit closer to the camera.
So one thing is that the camera is currently not lighting up.
Is it not lighting? Oh, that's going well. It's going well. This is what happens when you turn the Pi off before you start. Let's have a quick look and see.
So essentially, this is not really representative of how it would be done in the real world, as you may have already seen. So first of all, the resolution of our camera is not so great. And then also, we're using a Grafana dashboard, which in reality, you wouldn't really use Grafana to do like a real life thing like this, because the scraping is way too slow. So in reality, you might still use some sort of time series, but you would probably push this into a database, and then that would probably feed into some sort of platform that you're using in order to manage your data, or it could also be some other dashboards. Is it looking good?
It's not looking brilliant. This
okay.
We ironed out all the problems with this yesterday, and naturally now is the one time it decides not to work. We may have to just, down to time, move on with this
Actually,
one.
can I get the other slides up so I can just continue with the... Because I think there's actually a slide of our setup, so I can just talk about it while maybe it's going to start working, or you can just think about what it would look like if it was working.
Let's go back to where we were. Okay.
Yeah, over here.
Yeah.
I'm going to get this guy. Maybe you can try to bring it up. Maybe it's going to work if we all hope. So this is actually our actual setup. This looks similar to what you have seen previously. You can see that our device in this case is actually a Python pod. And this Python pod is running on our Edge device. So it is not necessarily exactly the same as you would see in a factory. This Python pod is containing this demo, this model, which is doing the shoulder line and the raised hands. And then it feeds through MQTT into the mapper. And this mapper, because it's already receiving MQTT, it doesn't really map anything. But in reality, you might have an actual industry protocol instead of MQTT that is translated into MQTT and then goes through the device twin back into the cloud. Do we have a light on the camera?
No, it's decided that today is not going to be its day.
Okay, maybe today is not the day. You can still raise your hand.
Yeah, feel free.
I really like it. Do you want to talk about...
I might as well carry on in that case, okay. Yeah, sure. So
sorry about that.
Not quite the demo we were after. So Antonia's already covered a lot of this, and so the device section at the bottom, in this case, running on the Pi, obviously it makes sense, but in this case it's a Python pod which is processing the camera footage. This, in reality, you would probably be a separate remote camera that's being accessed by some remote protocol. So just looking at the device itself, as we said, it's processing the camera feed, and then what it's doing is every time it detects a change in the number of raised hands, it's going to publish an update to the MQTT broker on a specific topic. So that, in theory, changes all the time, not in this case. The mapper itself is quite simple. It's just subscribing to the same topic that the broker is listening on, and whenever the Python app publishes a change, a message to the broker, it then consumes that, and then the mapper via KubeEdge is going to update the value of the device custom resource in the actual cloud cluster right up the very top. So down here, obviously, is where the edge processing would normally happen. So before your data gets pushed back to your central cluster, you're going to do your pre-processing here, which is essentially what the Python pod is doing. Normally, that would be there. And so you can think of this as like your satellite pre-processing before it downlinks to Earth, that kind of thing. And so for the purpose of this demo, you wouldn't do this in production, but we're also exposing the value of the count of number of hands as a metrics endpoint, which we're scraping via Prometheus and Grafana, which, if that had worked, you would have seen changing in Grafana. So if you want to take a look at this all for yourself, we've made the demo repo publicly accessible. There's a bunch of different bits and pieces in there. So there's the code for the mapper. So we took an upstream one, and we forked it a bit in order to make some changes to it, things like the metrics endpoint. The Python app that we've been using to process the images, alongside all the manifests we've deployed it with, and of course all the KubeEdge specific stuff, so the device and the device model custom resources. So if everyone's, I think, taken a photo of that, we can move on. So a little bit of a reality check. Quite a simplified demo, really, if it had worked. But still, each component of the demo does really map to the real-world use cases of the technology. So we can take a look at those here. So instead of counting hands, maybe think of this as we said before, maybe a camera in a factory that could be watching for defects in a product line, or you might have temperature or vibration sensors that are monitoring machine health. So in this case, the camera maps to some kind of industrial sensor. If it's going to be a camera, it will be some kind of remote camera that's being streamed over something like ONVIF or RTSP, remote access protocols. So the Pi, in this case, is our edge node. It would be an edge node. And this would be running the analytics models, which are analyzing whatever data is coming in. So the Python app is essentially part of the edge node at that point, because that's where you do your processing. So the mapper, as Antonia said, is an adapter for protocols. MQTT itself is actually already quite heavily used in industrial settings. But obviously, you can have many different device outputs that are then being translated from their native protocols into MQTT using, as we said earlier, something like Hive MQEdge that does that for you. And so the mapper in our demo, as we said, is subscribing to the MQTT messages that the Python app is outputting, but mappers can listen on any protocol. It's down to you how you write it, because that's where your business logic comes in. So the device twin are the two custom resources that represent devices. In our demo, they are quite comparable to a digital device twin that's already quite heavily used in industrial IoT setups anyway. And as Antonia said, we've got Prometheus and Grafana down there pulling the metrics, but you could use some kind of time series database or some other way of storing your data, and then feed that into something like a SCADA dashboard, some kind of cloud analytics platform that you're using to perform like predictive maintenance. So yeah, quite a simple demo, but quite clearly maps fairly well to actual use cases. And with that, demo didn't go so well, but we've reached the end of our talk, so thank you all very much.
So the first is quite simple. What are the minimum requirements on the edge, hardware and software, I guess, to run the platform in itself?
Yeah, so I guess that really depends on what sort of devices you want to be using at the end of the day. So we're running this on one of the latest Raspberry Pis, so fairly powerful. It's an 8 gig model, quite beefy, but we are doing heavy image analyzing on there. If you're just pulling information from sensors, a lot smaller. We've done this demo, not this demo specifically, but we've attached much older Raspberry Pis. Works absolutely fine. It needs essentially an OS, and then you bootstrap that, and then you join it to the cluster. The KEADM CLI that Antonia talked about does all the work for you. Provide it a join token and the target, and it does the rest of the work.
How does the KubeEdge device model compares to Avrillier?
I would say that the KubeEdge device model is maybe not that mature yet. There were some recent developments which are very interesting. So they have actually changed their API quite a lot. So I think it has a lot of potential, but also I think it's not maybe necessarily as evolved as enterprise solutions will be at this point.
Do I see the edge device as a real node in Kube API? If so, is the edge core acting as a sort of virtual kubelet?
Yeah, that is pretty much what is happening. So if you're going to list your nodes, you're going to see these nodes. They're going to be marked as edge. And it's not exactly the same, but you would not notice the difference at first. And then you have the edge-D component inside the edge core, which is basically the kubelet.
What happens if the database on the edge get corrupted?
In theory, it's much the same as any other Kubernetes node. You would recreate it. Obviously, there is data loss, but yes, there is the possibility of that happening. These are small, low-powered devices, so the chances of that happening are maybe somewhat greater than a decent, chunky VM.
Did you try turning it off?
Many times.
That would probably fix it.
That's right, absolutely.
Yep.
And Grafana works. Yes, we saw that. Why HTTP between cloud and edge instead of a secure protocol as default?
I think because if you are inside your own network, you might not necessarily care about it that much. However, you can also implement other solutions.
Can KubeEdge help me run workloads on edge devices as well? If not, what is the tool of choice if I like Kubernetes?
Yeah, so as Antonia said, the device side of things, you don't have to use that. You could just run containers on the Raspberry Pi as you like. I mean, that's basically what we're doing here. We have to process the data from the camera, we have a standard deployment, a standard Kubernetes deployment, and all it has is a device selector that targets the labels on that node, so they don't run on the kind cluster, it runs on the Pi itself. So yes, it's the same as using any other device, any other node in Kubernetes.
Is it open source? We saw that, so that's answered. Any experience with KubeEdge on LoRa gateways?
No.
As simple as that?
Yep.
What are the security considerations for Kubernetes at edge?
I personally would say much the same as when you're running it anywhere else. More so maybe on-prem. The things to consider with running it at the edge, obviously, is you have these devices. So if you're running it in the cloud, you've got nodes in a data center or in the cloud, whatever. Then physical access to them is fairly minimal. These sorts of devices potentially running in factories. You've got people in there who don't touch IT at all in general. They don't know what they're doing. These people maybe have access to those devices, so you do need to think about your physical access. But otherwise, I don't think there's that much difference between them.
Let's go for the 4 last question. How much data do you need to be transferring so it would pay off to adopt edge?
I think that's kind of a difficult one to answer. I think it's very much specific on your particular use case. Like we saw with the satellites, maybe that's very, very different to the devices that are running on the camera gantries. I think it very much varies on your workloads.
In a typical real-world scenario, which additional components, VPN, service mesh, are required to secure the connection between the edge hub and the core hub?
I guess this is kind of down to your security posture, to be honest, more than anything else. How you want to do it, you can leave it wide open, or you can put it through those tools. It's entirely up to you which you want to go with. Obviously, I advocate for encrypted and so on, but yeah, whatever you want to do with it.
And the next question is about SQLite and the difference between SQLite and etcd. We've seen SQLite shock under stress. It's not as performant as etcd. What's the limit on the number of devices it can handle per edge node?
That's actually a good question. I don't know the answer to this. However, I would assume that the goal of having the edge devices is to spread them out, so to not connect a bunch of devices all to the same edge device. But maybe someone has tried this out, I'm not sure.
I'd also say that the KubeEdge website has quite a lot of information on their benchmarking.
Oh, yeah.
So this is how they know that it can get to 100,000 nodes before they put it across all the gantries. They already benchmark it against these sort of numbers, so I would imagine that sort of information is probably on there somewhere.
How are image updates handled with flaky connections?
So I think this comes back to, as we said, the way nodes can disappear offline. The communication between the cloud core and the edge node itself is they buffer information, basically. So if that device goes offline, then when it comes back online, that gets handled with the buffer, the stored information. It's just down to I guess when the connectivity comes back.
Okay. We are sadly already over time, so they will not have any more questions. Thanks a lot for the great talk, and please have a round of applause for our speakers.
From ContainerDays Hamburg, this video is proudly presented by Dux IT.